Section 16.3, Fundamental Theorem for Line Integrals. Similar to our fundamental theorem of calculus, we have a fundamental theorem for line integrals, which says that if C is a smooth curve given by the vector function r of t, where t goes between a and b, and f is a differentiable function of 2 or 3 variables whose gradient del f is continuous on our curve C, then the line integral of the gradient of f dot dr is equal to f evaluated at the endpoints of our curve, f of r of b minus f of r of a. So just like our fundamental theorem of calculus. Let's see if we could prove this real quick. So we have our f, our function of 3 variables. We have c, our space curve, which joins point A given by x1, y1, z1 to a point B, x2, y2, z2. So our theorem becomes the line integral equal to f evaluated at the endpoint r of b is now just x2, y2, z2, and r of a is just x1, y1, z1, because that's where our points point to at those endpoints. So that means that we have the line integral of f dot dr, or del f dot dr, equal to the dot product of the gradient of f evaluated at r of t dotted with r prime of t dt, and pretty much by definition. So then the del f of r of t is just the partial f with respect to x, partial f with respect to y, partial f with respect to z. R prime, if we break it down into each of its components, is just dx dt, dy dt, and dz dt. So notice this is just the chain rule. This is really just the derivative of f with respect to t. If you want to go straight through, you can imagine that dx is canceling. Same thing for f with respect to t for y and f with respect to t for z. So really this is just the derivative of f of r of t with respect to t. And then we can just apply the fundamental theorem of calculus to go backwards and say that this integral of that derivative is really just equal to f evaluated at the endpoints. So it's really not that hard to prove. Let's see if we can do an example. We'll find the work done by the gravitational field f of x equals minus mg over the length of x cubed times x in moving a particle with mass m from the point 3412 to the point 220 along a piecewise smooth curve C. So as we saw in example 16.1.4, we have the force field F written out in terms of each of its components as mmg times x over the x squared plus y squared plus z squared to the 3/2 power, and then there's y over that, and then z over that for each of the components. So it looks like that's just the derivative of the function f without each of those in our numerator. In other words, we have our vector field f equal to a gradient where f is equal to mg over the square root of x squared plus y squared plus z squared. Because remember, our gravitational field F was equal to this thing where we had an x and then this thing cubed. But if we want to just get back to F before we take our partial derivatives, we could just remove that x and just change this to the 1/2 power instead of the 3/2 power. Okay, so now we can actually use our fundamental theorem for line integrals. Notice that for the fundamental theorem, we don't have capital F dot dr unless we happen to manage to replace that with del f for some gradient equal to our vector field. So finding this potential function is essential to being able to use the fundamental theorem. If we can't find such a function that has its gradient equal to our vector field, then there's nothing for us to evaluate at endpoints, because we can't evaluate our vector field at the endpoints. We have to evaluate our potential function at the endpoints. So not only do we need our vector field to be conservative in order to use this, but we actually have to know what the potential function is. But in this case we do. So our work is equal to the line integral over c of f dot dr, which is equal to line integral over c of del f dot dr, as we just saw, with f equal to what we just wrote out. So that's just going to be f of 2, 2, 0 minus f of 3, 4, 12 by our fundamental theorem for line integrals. So that's mmg over the square root of 2 squared plus 2 squared, and then plus 0 squared, so we don't have to worry about that, minus mmg over the square root of 3 squared plus 4 squared plus 12 squared. And that's mmg times 1 over 2 rad 2 minus 1 over 13. So now that we have our fundamental theorem for line integrals, there's actually a lot of other results that we can connect to it. In general, if f is a continuous vector field with domain D, we say that the line integral f dot dr is independent of path if the line integral over some curve C1 is equal to the line integral of some curve C2 for any two paths C1 and C2 in our domain that have the same initial points and the same terminal points. In other words, if we have a path that starts in somewhere and ends in somewhere, and we integrate over it, then our line integral would have to be an identical line integral to the one that we get when we integrate over a totally different path, as long as that other path happens to start and end in the same place as the first path. So it doesn't matter if it does something insane. If it starts and ends in the same place, then the line integral over this thing would be the same as the line integral over this thing. Or if I had an insane path like this versus a nice smooth path like this, because they both start over here and end over here, the line integral over this mess would have to be equal to the line integral over this nice smooth part, no matter how crazy it becomes. So line integrals of conservative fields are automatically independent of path, because as we noticed, when we have a conservative field, then we have a potential function. Our vector field is the gradient of some potential function, so we can just set that equal to that function evaluated at the endpoints. So that's the only thing that contributes to the value of the integral. Next up, we'd say that a curve is closed if its terminal point coincides with its initial point. So that means that r of b is equal to r of a. So in this figure over here, we have a closed curve. F dot dr is independent of path on D if and only if the line integral is 0 for every closed path. So let's prove this real quick. If the line integral is independent of path in D, remember we have an if and only if, so we have to go both directions. We have to show that if it's independent of path, then that forces the line integral to be 0 for every closed path, and we have to also show the other way. If we have line integral 0 for every closed path, then that forces it to be independent. So first we're going to do one direction where we assume that the line integral is independent of path. Okay, so we'll make C any closed path. We need to show that the line integral will be 0. So if C is any closed path, we can choose any 2 points A and B on C as being composed of the path C1 from A to B, followed by the path C2 from B to A. So here's C1 from A to B, and here's C2 from B to A. So then our line integral over C is equal to the line integral over C1 plus the line integral over C2, just by linearity. But the line integral over C2, it's the same thing as if we went backwards over C2 and we threw in a minus sign. So we'll put in minus for C2 and we'll change the plus to a minus. And then we get this over here. But remember, we were assuming that we were independent of path. Minus C2 and C1, this is minus C2 in that direction, and this is C1 over here, they both have the same endpoints. So that means that this line integral must be equal to this line integral. So it's like subtracting the same thing from itself, it must be 0. Okay, so we've shown that if it's independent of path, then the line integral must be 0 over closed paths. So how about we now show that if the line integral is 0 whenever c is a closed path, then we have independence of path. So let's assume that. We're assuming that the line integral is 0 over any closed path. We'll take two paths c1 and c2 from a to b. So let's see if I can draw that. It's not pictured over here, but it's a pretty similar picture. So let's say here's A, and let's say here's B, and we can make this one path. That could be our C2 in this case, and this could be our C1. So they both go in this direction from A to B now. Okay, and we want to define C to be the curve consisting of both of these guys. So C will be the curve consisting of C1 followed by minus C2, because notice C2 is going from A to B, so if I want to keep going over here, I have to put a minus in to flip this arrow over here to the other direction. So that means that because we have our line integral 0 over any closed path, that means that the line integral over C must be 0. And remember, that's the line integral over C1 plus the line integral over minus C2, because we keep going in this direction, minus C2. But minus C2 is the same as integrating over C2 as long as I throw in a minus. So I can throw in another minus here, another minus here. These two minuses cancel, become plus, because I'm just changing direction. So I end up with a minus over here and line integral over C2. So that means that 0 is equal to the line integral over C1 minus the line integral over C2. So I'll just move this to the other side, and I get that the two line integrals are equal. So we are independent of path. Okay, so a little bit more. Suppose F is a vector field that is continuous on an open connected region D. By open, we mean that for every point in D, there is a disk with center P that lies entirely in D. And by connected, we mean that any 2 points in D can be joined by a path that lies in D. So if I have I don't know, some disk like this, like let's say this was x squared plus y squared less than or equal to 1. If I was looking at a point P in D, let's say over here, then I could draw a disk around it. So that point satisfies what we need for our region D to be open. However, not all of the points do, because if I were to choose a point over here on the boundary, that circle, then any disk I draw will not be contained entirely within D. It escapes a little bit. So then in this case, this is an example of region D that's not open. So in order for this thing to be open, what I could do is make this less than 1. And what I could do is make this thing dashed, just to indicate that I'm not including the boundary points. And then no matter what point I choose inside, I'd be able to draw a circle around it that's stuck in here, because I'm not allowed to pick points over here on the boundary. So this would be an example of an open region. It also happens to be connected because any point that I pick anywhere else, if I pick a point here and a point here, I can connect them with some path. So as long as we can connect them with a path, we say that that means it's connected. At least for our definitions that we're going to use in our calculus sections. In topology, you probably use different definitions and try to make things a little bit more general. You might say that it was path connected instead of connected, but it's okay. We're just doing exactly what we need to just keep going. If our line integral is independent of path, it turns out then F is a conservative vector field on D. That is, there is a potential function. So this is not the easiest thing to prove. Notice that we said before that if we have a conservative vector field, then we take the line integral, then we are automatically independent of path. However, the reverse is not necessarily true. If we're independent of path, we're not necessarily conservative. We need a little bit of an extra criteria. That's why we had to talk about our open and connected region over here. We didn't need that in the other direction to say that if we have a a conservative vector field that we're independent of path, but we do need it if we want to go from independent of path to conservative vector field. So it's a little bit harder to go in the reverse direction. So in order to do that, what we basically would do is we would build some function f of xy equal to the integral from some fixed point AB to the point xy of f dot dr. We basically integrate to build our potential function, and we'd show that it works and that it exists, and then everything's all nice. It's a little bit of work, but we are going to use the technique, that general idea of going backwards and integrating to find potential functions. So we have basically a converse that unites everything together and says that conservative vector fields, when we integrate, they're independent of path in either direction, but if we go backwards, we have to be very careful that we are in an open connected region D, so it's not a perfect converse. So last but not least, if f of xy equals pxyi plus qxyj is a conservative vector field, where p and q have continuous first-order partial derivatives on a domain D, then throughout D we have the partial of p with respect to y equal to the partial of q with respect to x. This is pretty easy to prove though. So how would I do that real quick? If we have a conservative vector field, then that means that f must be the gradient of some other potential function. So that means that these guys must be partial derivatives of some other potential function, because these are the components. So that means that p must be equal to the partial derivative of f with respect to x for some potential function f, and q must similarly be the partial derivative of f with respect to y. So that means that we can take the partial of p with respect to y and get that it's going to be the second partial, so this is a 2 over here, of f with respect to x and then y, and that's equal to the second partial of f with respect to y and then x by Clairaut's theorem, equality of mixed partials. So, because remember p and q have continuous first order partial derivatives, so that means that this is equal to the partial of q with respect to x, which is exactly what we wanted to show. As before, the converse of this is not so easy to prove. So we're saying that if we have a conservative vector field, and that forces the partial of p with respect to y to be equal to the partial of q with respect to x, but wouldn't it be great if, when this happened, that forced our vector field to be conservative? If we could go backwards. And it turns out we sort of can, just like over here, but we have to make another big assumption. We have a partial converse assuming certain criteria we can go backwards, and the converse is even then not so easy to prove. So in order to talk about that converse, we have to say what it means to have a simple curve, and that's a curve that does not intersect itself anywhere between its endpoints. So here we are simple, here we are not simple because it intersects. This one's not closed because it doesn't start and end in the same place, but this one is. And this one is not simple and not closed because it twists over here in the middle. So now that we know what a simple curve is, we need to talk about what a simply connected region is. And that's a connected region. So remember, that means that we can connect any points inside with a path. But it's also a region in which every simple closed curve encloses only points that are in D. So in other words, if I draw a simple closed curve like this, then the inside of it must be inside of my region, which is a fancy way of basically saying that there are no holes and no separate pieces, because in this case it wouldn't even be connected because I couldn't draw a path from here to here. Okay, so now we can write our converse. Suppose that we have f equal to pi plus qj. It's a vector field on an open, simply connected region. Let's suppose that p and q have continuous first-order partial derivatives. Then f is conservative if these guys are equal. Okay, so having these guys equal now will tell us it's conservative as long as we have certain criteria, and if it's conservative, we don't even need those criteria, we're guaranteed that these guys are equal. So the major upshot here is we have a way to tell if vectors are not conservative, which is super easy. We just check to make sure that the partials are not equal, because if it was conservative, they'd have to be equal. And we have a way to check if vector fields are conservative, but in that case, we have to check the converse. So we have to make sure that we have an open and simply connected region. So let's do some examples. First, let's see if this vector field is conservative. So let's look at p of xy, our first component function, which in this case is x minus y. And we'll look at q of xy, which is x minus 2. And we'll look at the partial of p with respect to y. Notice that's minus 1. The partial of q with respect to x is equal to 1. So that means that the partial of p with respect to y is not equal to the partial of q with respect to x. So that means f is not conservative by the contrapositive of the first theorem we looked at. So that was what said that if we have a conservative vector field, then it must be that these partials are equal. We just saw the partials are not equal, so there's no way that our original vector field was conservative, because if it was, they would have had to be equal. That's contrapositive. Okay, so now let's do another example. How about we see whether this vector field is conservative? So again, we will write out p of xy, and that's equal to 3 plus 2xy. And we'll write out q of xy, and that'll be x squared minus 3y squared. So let's see about our partials. We've got the partial of p with respect to y equal to 2x. But that's also the partial of q with respect to x. So they have partials that are equal. That doesn't necessarily mean our vector field is conservative, though, because our converse was not as powerful. We needed more of an assumption. Remember, we need to make sure that we're on an open and simply connected region also. So let's check that. Our domain D is everything we can plug in here. Notice we can put in anything. These are polynomials. So our domain doesn't have any missing values, so we don't really have to worry. It's all of R2. It's the entire plane. And the entire plane is definitely open and simply connected. You can draw a circle around any points inside that'll still be in there. You can draw paths, and any simply closed curve will not have any holes, cause any holes. So that means that f is conservative using both of these criteria. So that means that there is some potential function where we could take the gradient and get f. Okay, notice this is the same function we just looked at. We just showed that this thing is conservative. So because it's conservative, we know that f is equal to del f for some potential function. So it makes sense we'd want to try to figure out what that function is. So in the way that theorem over here that I briefly mentioned, that says that if we have a vector field continuous on an open connected region, then f dot dr is independent of path. So we find this potential function. That's sort of what we're going to do over here. We're going to integrate and go backwards. So let's start with this thing over here. It must be equal to partial derivatives because it's conservative. There must be some potential function. So I could say that the partial derivative of that function must be equal to this first component with respect to x. So that's 3 plus 2xy. And there must be some function with a partial derivative with respect to y that is equal to this component, x squared minus 3y squared. We don't know what that function is, but it must be something that has partial derivatives to satisfy these criteria. So how about I kind of do a partial integration? I'll go backwards from this. So I'll end up with our function, our potential function f of xy equal to, instead of 3, I'm going backwards with respect to x, so I get 3x, taking antiderivative. Instead of 2xy, I get x squared y, because y is constant. However, I have to be a little bit careful. Integrating 0, like a plus 0 you can imagine is over here, could give me a constant, but it could also give me a y, because if I took the partial derivative with respect to y, this would disappear. It could even give me a y squared. It could give me something crazy with respect to y. So it could give me any function of y. It could be a constant function. It could be anything. When I take the partial derivative of this thing with respect to x, this would disappear. So I need to figure out what that function of y is in order to actually complete my formula for my potential function. So I've used the fact that the partial with respect to x is equal to this, but I haven't even used this fact yet. So how about I take this function and I will partially differentiate with respect to y. So I'll get, well, 3x will disappear because it's constant. This is the variable now, so I just have the constant x squared. And the derivative of g of y would just be g prime of y. So let's compare this with what we know our partial derivative with respect to y must be equal to. It must be equal to x squared minus 3y squared. But we saw it's equal to x squared plus g prime of y. So now we know g prime of y must be equal to negative 3y squared. So this implies that g prime of y is equal to negative 3y squared. So again, we can anti-differentiate. We'll get g of y by going backwards. That'll be negative y cubed if we anti-differentiate with respect to y, plus some constant k. There's no way that it could be a function of x at this point, because this thing was a function of y to begin with. So I think we're pretty much good now. We have our potential function f of x y equal to 3x plus x squared y plus our function of y we figured out is minus y cubed plus k for some constant k. And you could test this. You could take the partial derivatives and you could form the gradient of this thing, and you would see the gradient is actually equal to this vector field right over here. So the cool thing is, now that we know how to find potential functions, we can potentially use the fundamental theorem of line integrals. So we just have to find the work done by plugging into our potential function at the endpoints. So let's see what our endpoints are. We're going from 0 to pi for this line integral that we want to do. So that means that we need to look at r of 0, which is equal to 0, 1 if we plug in for our endpoints, and we need to look at r of pi. So we'll plug pi in and we get 0 minus e to the pi. So that means that the line integral over c of f dot dr must be equal to the line integral over c of del f dot dr, because we showed that f is conservative, and then we even found the potential function for f. And this is just going to be that potential function f evaluated at our endpoints, f of 0 minus e to the pi minus f of 0, 1. So plugging that into our potential function that we came up with over here, notice we're doing the fundamental theorem. Just like in the fundamental theorem of calculus, it didn't matter what constant you chose. So we always just chose c to be equal to 0 to be convenient. So we can just choose k to be 0 because it'll cancel when we subtract anyway. So we'll choose k 0 and we'll plug in 0 minus e to the pi for x and y, and then we'll plug in 0 and 1 for x and y, and we'll subtract. And we get e to the 3 pi minus 1, which is e to the 3 pi plus 1. So much easier way of evaluating line integrals, assuming that you have the potential function so that you can apply the fundamental theorem. So there's nothing really special about 2 variables versus 3 variables. It just makes it a little bit more time consuming to find potential function. So let's do an example of that. As before, we'll take each of our components and we'll set them equal to partial derivatives of that potential function, because if this thing is conservative, then it must exist. And if the problem is telling us to find the function f such that del f is equal to f, we're going to assume that this function exists and that it's not a trick question. So we'll say that the partial with respect to x of x, y, z is equal to y squared. We'll say that the partial with respect to y is equal to 2xy plus e to the 3z. And we'll say that the partial with respect to z is equal to 3y e to the 3z, just by reading off of our components. So this means that if we integrate with respect to x, we'll do our partial integration, we get xy squared plus some function of, well, let's see. It's not just going to be a function of y this time, because there's z's that could be in there too. If I had a y and I took the derivative, it would be 0 and disappear. If I took a z and took the derivative, it would be 0. If I took z squared, it would be 0. And if I took y squared z squared and took the derivative, that would be 0, because I'm doing it with respect to x, so this would be constant. So I need to accommodate for all of those possibilities, so I need a function of both y and z in this case when I take my antiderivative. So that means that I need to figure out what this function of y and z is in order to complete my potential function. So we've used this partial with respect to x, we have not used the y and the z's yet, so we're probably going to have to use both of those. First, let's take the partial with respect to y and then compare it as we did before. So if we take the partial with respect to y, we get 2xy plus the partial of g of yz with respect to y, so that's gy yz. And we can compare that to what the partial with respect to y is. Notice there's a 2xy in both, so the extra bit is e to the 3z. So that's what our partial derivative with respect to y must be equal to. So this implies that gy of yz is equal to e to the 3z. And we will anti-differentiate with respect to y. We get g of yz must be equal to ye to the 3z plus, well, we have to be a little bit careful here. It's not going to be a constant this time, because it's going to be a constant with respect to y maybe, but with respect to z, it could be any function of z. Because if I put a z over here and I went backwards differentiating with respect to y, then it would disappear. Z squared, 10z squared, whatever it is, it would disappear. So I need some function of z. So I'm not done yet. I went from a function of yz to a function of z. I still need to figure out what that function of z is. So far, let's write out the progress we've made. We've figured out that our potential function is xy squared plus ye to the 3z plus h of z, because we replaced g of yz with that. So we're making progress. We just need to figure out what this h of z is. So let's use the last thing that we didn't use yet. We'll take the partial with respect to z. So fz of xyz is equal to 3y e to the 3z plus, so notice this is just gone because it was constant with respect to z, plus h prime of z. The derivative of h of z with respect to z is just h prime. Okay, so this is awesome because notice we have 3y e to the 3z equal to this partial. There is nothing extra. So that means this thing must be 0. So we don't have to worry about it that much. We have h prime of z equal to 0. Anti-differentiating with respect to z, we get that h of z must be some constant k. So now we're pretty much done. We have our potential function, equal to xy squared plus ye to the 3z. And notice our function h of z is just our constant k, and that's our potential function.